All right, hi guys, Mr. Rocco again. This is going to be the second video for this week, the week of January 4th. The first video was on the definition of what insolation is. Again, it's sunlight or energy that the sun gives us, we receive from the sun. This one is on what happens to sunlight when it reaches the atmosphere. So let's jump right in. So it says when insolation, again sunlight, enters the atmosphere, it can do one of three things. It can reflect, it can scatter, or it could be absorbed. Reflect means to bounce off, right? It'll come in and then bounce right back into space. Scatter means it kind of spreads out. It'll go in all different directions. Absorb means to take in, to soak it up. And so again, as we talked about in the first video, I like my little sun up here. That's from, what's that show? Teletubbies. That's it. If you're ever familiar with Teletubbies. Anyway, clouds will reflect 21% of the sunlight. So as that insolation comes in from space and hits clouds, like on a day like today, Sunday, again, it's cloudy, overcast as approaching snowstorms coming in. Clouds are going to reflect 21%. And it's going to go right back up into space. It's also going to absorb about 3-4%. That's going to get soaked up in the cloud. So again, about 1/4 of all the sun's energy is going to be either reflected or absorbed by clouds, which never makes it to the ground. Ozone. Again, we talked a little about that in the first video. Ozone's job is to absorb the ultraviolet rays. So you've got UVA and you've got UVB. Its job is to soak up those ultraviolet rays so that they don't reach the surface to affect humans. Ozone sits, and this is on your reference table, page 14, the atmospheric layer chart, which we've looked at earlier in the year. Here's the stratosphere. You're talking, this is, let's see, 5, 10, 15, 20, 25. So you're talking anywhere from 15, 20 miles up, let's say. Roughly 20 miles up into the atmosphere is where the ozone is going to sit. There's a layer up there in that stratosphere that's soaking up those ultraviolet rays. They will ask that question on the regions. Typically, they'll ask something like, what is the primary purpose of ozone? What's its job? What's its function in the atmosphere? And its job is to soak up the ultraviolet rays. Aerosols. Aerosols are going to be little dust and droplets, molecules, water droplets up in the atmosphere, billions and billions and billions of particles up there in the atmosphere. They're going to cause sunlight to get reflected, some of it, bounce back into space, or scattered, kind of spread out. Ice and snow. So we don't have any on the ground as of this video, but tonight, I think, this is Sunday, so Sunday night, we're supposed to get, I saw 1 to 3, 2 to 4 inches of snow. So Monday morning when you wake up, if there's a few inches of snow on the ground, that ice and snow, right, being a white surface, is going to reflect that sunlight. And so that will cause reflection, which actually will lower your temperatures. So let's say the forecast tomorrow is to get up to, let's say they're predicting the high temperature tomorrow is supposed to be 40 degrees. But now tonight it snows and we get 2, 3, 4, 5 inches of snow. That now will cause tomorrow's prediction for 40 to drop. And we might not get to 40 tomorrow. We might only get to 35 degrees. So you might have to take 5 degrees away from that forecast, because now with a snowpack on the ground causing reflection of the sunlight, right, it's going to keep your temperatures lower. And so sometimes meteorologists will have to adjust forecast for high temperatures as we move on in the week, and if you get snow one night, like let's say tonight, they're going to lower those forecasted temperatures because of the reflection. Clouds. So again, clouds not only reflect, but they also absorb infrared, which is heat. So clouds, and I touch on this, every year with my students. Clouds actually have two purposes, two roles. A day like today, when it's cloudy out, yes, they are doing this up here. They are blocking the sunlight, causing reflection, keeping temperatures down at the surface cooler, right? It's not going to get as warm today as it did yesterday on Saturday. Yesterday got up to, I think, like I said, almost 50 degrees. Today won't get up to 50 degrees because the clouds are blocking the sunlight. So that's purpose number one, or rule number one. Rule number two, cloud's job is to act like a blanket, right? You go to sleep at night, you cover your body with a blanket. Well, why do you do that? Just because you're told to put a blanket on? What's the purpose of the blanket? Well, the blanket's job, because you're asleep and your body is still laying in a bed, you're not creating any energy. And so your blanket's job is to absorb the infrared. Infrared is heat. Any heat that your body is giving off at night while you're asleep, which isn't much, right? You're not moving, you're not running, you're not walking, you're not doing any exercise. You're just laying there in a bed asleep. So the minimal amount of heat that your body is giving off, you don't want to lose for those 8 hours that you should be sleeping. And so your blanket's job is to trap that heat. Well, that's what clouds do. Clouds, I call them Earth's blanket. When we have a cloudy night, the job of the clouds is to trap any heat that the Earth gives off. So the Earth is going to lose heat. Waves of heat are going to escape from the surface of the Earth, as I'm drawing these arrows. If there are clouds up here, their job is to stop that heat from leaving, from escaping. That will actually keep your temperatures warmer at night. Just like a blanket keeps you warm at night, that's the job of a cloud, is to keep the Earth's temperatures warmer at night. And I have a video I have to find, or not video, a picture. Here it is. So you might hear meteorologists from time to time talk about this when they're talking about nighttime temperatures, especially this time of year. It's called radiational cooling. Again, radiation just means energy, and cooling is cooling. So it depends on what kind of night that you have will create a different situation, whether it's really cold in the morning when you wake up or not too bad. And it goes from left to right. If you go from this side of the diagram over to this side of the diagram. So if you start over here, less cooling potential. This means at the next morning when you wake up, you say, oh, it's January, Mr. Rocco, but it's not that cold this morning. Why is that? We had clouds. So here's the first situation. Clouds act like that blanket, and they block heat. So the heat will not be able to escape the Earth. It's going to stay trapped down here at the surface, just like you put a blanket on at night to keep you warm. So that's going to keep the Earth, air quotes, the warmest possible the next morning on a cloudy night. Let's say you don't have any clouds, but you have wind. You have a little bit of a breeze. Well, that wind actually will also cause a blocking situation and not allow the heat to escape. So it might be a clear night, but it's a breezy night. The wind will stop the heat from being able to escape from the surface and go into space. And so that's going to keep the Earth also warmer. Not as warm as the blanket with clouds, but still fairly warm. Then, let's say you go to this situation. This is like scenario 1. This would be scenario 2. We're into scenario 3. Clear skies, calm winds. So not only is it clear, but there's no wind. Well, that's going to allow for a lot of heat loss. There's nothing to stop the heat from leaving the Earth and escaping, and therefore in the morning, you're going to wake up on a clear night with a very calm wind, and you're going to wake up the next morning, and its temperature's going to be pretty cold. Frost on the car, frost outside, on the grass, etc. And then, of course, the most cooling or the coldest morning would be not only with the clear skies and the calm winds, but you have snowpack on the ground. So again, let's say we get some snow tonight, and then this week we have a clear night coming up, let's say Monday night or Tuesday night or whatever, and we still have a few inches of snow on the ground, and we have clear skies, calm winds, and now snow cover on the ground. You're going to wake up the next morning and say, whoa, Mr. Rocco's right. It's going to be pretty cold the next morning. You might get down into the teens, right, or single digits in the morning because of all that heat loss as the Earth is losing that heat and escaping into space. So this gives you just 4 scenarios there, from how do we have a warmer morning when we have blanket of clouds to, wow, it's really cold this morning. It's snow on the ground and it was clear skies last night. All right, aerosols. So aerosols are small particles of dust, pollution that gets suspended in the air, and there's billions and billions of particles. Usually I refer to, let's say your house, if it's, let's let's say a bright sunny day, and you ever look out one of the windows of your house, or you see those crepuscular rays, you see those rays of sunlight coming through the window into your house. And then if you look at those rays of sunlight coming through a window in your house real carefully, you'll see little floating dust particles in your house. And no matter how much you clean, no matter how much you dust, no matter how much you vacuum, some people are very, clean freaks, and they got to really clean 24/7. No matter how much you do that, dust is still going to be there. And if you look at that sunlight, you can see those dust particles floating in the air. And so they're in your house. And if they're in your house, believe me, there's millions of times more in the atmosphere. And so let me click on these videos here. These are going to show you different aerosols. Some aerosols are natural. Some aerosols are man-made. Hold on, I'm just going to pause that. So what you're going to look at here, they're going to show you aerosols, different ones. Dust, you're going to see like smoke from fires, forest fires. You're going to see fossil fuels, sulfates. That's, I believe, the white ones. You're going to see sea salt, salt off the ocean, which is a lot of these. Some of these are natural. The white that you're going to see is not natural. That's your burning of your fossil fuels, but those are aerosols. The dust is the orange. The green is going to be some of your smoke from your fires, forest fires, wildfires. And this is just going to show you as a time lapse here. So let me get that going again. Oops, sorry, I must have hit the pause button. Hopefully it picks up where I left off. So anyway, this video is going to show you different aerosols. Some are natural, some are man-made. It's going to show you dust from, the deserts, smoke from wildfires, sulfates coming out of burning of fossil fuels, and even sea salt coming off the oceans. So let me play this for you. Okay. So, what I wanted you to take away, you can see the fossil fuels, China, Europe, United States, all that white. Again, some aerosols are natural. There's nothing you can do about that. The sea salt off the oceans, the dust coming off the Sahara deserts, things like that. Forest fires, yeah, that's something that's definitely a concern. But I just wanted to show you that one. Let me pull up the other video. This is also going to show you carbon dioxide. And this time of year, actually, carbon dioxide levels are much, much higher, and that's because of the trees without the leaves, right? They're not soaking up the CO2. And so let me pull this video up here.
Hi, this is Bill Putman. I'm a climate scientist at NASA's Goddard Space Flight Center. What you're looking at is a supercomputer model of carbon dioxide levels in the Earth's atmosphere. The visualization compresses 1 year of data into a few minutes. Carbon dioxide is the most important greenhouse gas affected by human activity. About half of the carbon dioxide emitted from fossil fuel combustion remains in the atmosphere, while the other half is absorbed by natural land and ocean reservoirs. In the Northern Hemisphere, we see the highest concentrations are focused around major emission sources over North America, Europe, and Asia. Notice how the gas doesn't stay in one place. The dispersion of carbon dioxide is controlled by the large-scale weather patterns within the global circulation. During spring and summer in the Northern Hemisphere, plants absorb a substantial amount of carbon dioxide through photosynthesis, thus removing some of the gas from the atmosphere. We see this change in the model as the red and purple colors start to fade. Meanwhile, in the Southern Hemisphere, we see the release of another pollutant, carbon monoxide. This is a gas that's both harmful to the environment and to humans. During the summer months, plumes of carbon monoxide stream from fires in Africa, South America, and Australia, contributing to high concentrations in the atmosphere. Notice how these emissions are also transported by winds to other parts of the world. As summer transitions to fall and plant photosynthesis decreases, carbon dioxide begins to accumulate in the atmosphere. Although this change is expected, we're seeing higher concentrations of carbon dioxide accumulate in the atmosphere each year. This is contributing to the long-term trend of rising global temperatures. The Orbiting Carbon Observatory 2, or OCO2, will be the first NASA satellite mission to provide a global view of carbon dioxide. OCO2 observations and atmospheric models like GEOS 5 will work closely together to better understand both human emissions and natural fluxes of carbon dioxide. This will help guide climate models toward more reliable predictions of future conditions across the globe.
Okay, so I just wanted to show you that with the CO2 levels. All right, so when you're talking about CFCs, CFC stands for chlorofluorocarbons. Chlorofluorocarbons. They're actually a compound. They're made of 3 elements: carbon, chlorine, and fluorine. And these are very harmful. These are aerosols that are put into the atmosphere that contribute to climate change. Now, luckily, back in 1996, January 1st, 96, Congress passed what was called the Clean Air Act. And that stopped the production of a very harmful CFC refrigerant called R12, R standing for refrigerant 12. And this was what they call it Freon. And this particular R12 Freon had the CFCs in it, which was contributing to pollution in the atmosphere, and of course it contributing to climate change and temperatures rising. And so since 96 they've stopped the R12 production. And cars and refrigerators used to use R12 refrigerant. And so I remember my first car was a 1984 Chevy Cavalier, and the air conditioning wasn't very cold, right? It was pumping out warm air. And so you used to be able to go to the auto parts store and buy a can of R12. And it was like $5-6, and you'd put that into the air conditioning system. But unfortunately, you had to hook the hose up to the system under the hood, and it would leak some of it out, etc., and that would pollute the atmosphere. Refrigerators too use a refrigerant. That's what keeps them cold. And so these refrigerants, R12, were polluting the atmosphere. And again, in 96, Congress said, enough is enough. We have to switch to some other cleaner form of refrigerant. And so now if you go to places like AutoZone or even Walmart, the auto section of Walmart or something, you will find refrigerant, but you're not going to find R12. I believe the new one is, or newer one, cleaner one, is called R34A, which is what you're going to find a can of in AutoZone or Walmart. That has no CFCs in it, CFC free. A lot of your spray products, like if you have a bathroom, let's say spray, or some of you might use spray deodorant, things that have sprays, they used to have these CFCs in them as well. And again, after 1996, Congress passed that Clean Air Act. And now you'll notice if you look at a lot of your cans, let's say you go around your house and find a spray can of something, and it'll have at the bottom of the can, right, let's say this is the can, somewhere down at the bottom, there'll be this little circle down there or some kind of writing at the bottom that'll say it does not have the CFCs in it, and it doesn't have the chemicals that deplete the ozone layer. These CFCs would attack the ozone layer and cause depletion of the ozone layer, which of course is now going to allow more ultraviolet rays into the surface of the earth. And so that was taken out of there. So spray cans, paint, insect repellents, deodorants, spray foam, you ever use that expansion foam stuff? Any of those used to have the CFCs in it, which is, again, eating away at the ozone layer, these CFCs. And now, after 1996, now you won't see those in those products anymore, including cars. Cars are going to be, the air conditioning systems are not going to have the CFCs in them anymore. Now, if somebody has a classic car, you still have, let's say, a 1970-something Chevy or Camaro or Corvette or something. Those air conditioning systems, anything prior to 1996, might still have the CFCs in them, refrigerants. The R12, I should say. This we looked up, I think it might have been last year. A student said, can you buy R12? Let's say you have an older car system. And I did. I went on eBay. If you go on eBay, you might search for R12 refrigerant, and you can see this person was selling 6 cans of R12 refrigerant for $150. Now, you got to remember, this stuff back in the 1980s when I was a teenager and had my first car, you could buy one can for, like I said, maybe $4 or $5. So this might have cost you $30 for all 6 cans. Now it's $150, right? Because it's a banned product, but people obviously still have some of this stuff floating around in their garages and are trying to make a profit on it because it's in short supply. Here was my first car. Well, that's not my first car, but that's what it looked like. Mine wasn't blue. It was a sort of like this metallic brown color. But anyway, this was my first car, an 84 Cavalier. And again, the air conditioning system used to use R12 refrigerant. But now it's not R34, R134A, I should say, is the ozone-friendly refrigerant that's now in the newer cars after 1996. Now, when sunlight enters our atmosphere, and this is where it gets into how is the air actually heated. The sun rises in the morning, right? But the temperatures aren't hot right away. And what I usually refer to is think of the earth like an oven, right? Let's say you're going to bake some cookies. You're making the dough, you're getting everything ready, you're going to make chocolate chip cookies, you're mixing in the chocolate chips, etc., etc. But before you bake the cookies and put the dough in the oven, what do you have to do to the oven? Right, you have to preheat it. Right? You got to turn on the oven and get it hot. So think of the earth like an oven. When that sun rises every morning, you look east, here comes the sun. Is it hot right away? No. You have to go through so many hours of the day, in the morning especially, before the temperature reaches its maximum. In fact, we usually don't reach our peak temperature until after noontime. 1 o'clock, 2 o'clock, 3 o'clock in the afternoon is usually when we reach our high temperature for the day. Why? The earth has to be, air quotes, preheated all morning long. The sun rises and it's like turning on the oven. But it takes all morning for the sun to heat the atmosphere. And the sun isn't really heating the air, it's really the earth. And that's what this slide talks about here. So what actually happens is the sunlight that's coming in, that's called insolation. We talked about that. That energy coming in is short wave. So let's draw a picture here. Let's say this is the ground. Let's say the sun's up here. You have to excuse me, drawing with a mouse is never easy, but do my best. The sunlight coming in is a short wave. Insolation is short wave, which means more energy, right? More potent. It's going to go into the ground. So the ground is going to soak up this sunlight. It's going to take that sunlight and turn it into heat, which is also known as infrared. And then heat waves, infrared waves, have to come out of the ground. Now, they're going to come out in a longer wavelength. They're not as powerful, right? The Earth doesn't shine like the sun does, right? The sun is a much more powerful force of energy. So those sun waves coming in are short wave, and those waves coming out of the Earth are longer wave. You have sunlight going in, goes into the ground. The ground has to soak up that sunlight. It has to then do a little conversion. It has to change it into heat. And then heat waves will come out of the ground. You can sometimes see heat waves. Picture a hot summer day. You're walking down a road. You're going, let's say you're walking up Route 9. You're walking from the village up toward Tops and Williams Lumber. And it's a hot, hot day. And you start looking down Route 9 on a hot summer day. You can actually see coming out of the blacktop heat waves. Right? I've never seen that before. Pretty cool. Those are heat waves coming from the blacktop, which is also going to happen out of dirt as well. But any surface like blacktop or the ground has to take sunlight, soak it in, turn it back into heat, and then spit it back out. When it spits it out and the heat waves come off the blacktop or out of the ground, that's called terrestrial radiation. Terrestrial just means Earth, right? Terrestrial planets, Mercury, Venus, Earth, Mars, right? We are a terrestrial planet. And again, radiation just means energy. So it's Earth giving off energy, right? We give it off in the form of infrared, heat waves. Football, I'm a big football fan. Let's say it's a cold, cold day and the football players are out there playing, right? And you got these 350, 380-pound linemen out there, these offensive linemen, and they're out there sweating, playing, getting hot. And, right, they all of a sudden now have to step off the field, right, switch offense, defense, whatever, and that lineman goes off to the sideline and sits on the bench. And that guy takes his helmet off. I don't know if you ever see this on a cold day. What's going to happen? You're going to see nice heat wave, steam coming off the guy's head, right? Is he angry? No, he's giving off heat, right? He's got all that heat that he built up as he's out there playing football. He takes his helmet off, and all of a sudden the heat waves start coming right off the top of his head, right? That's infrared. So you and I are constantly giving off infrared. You just might not see it. You might on a cold day, or like a football player would see it. Or again, you see the heat waves coming off the blacktop on a hot summer day, right? Those are infrared waves. But that all takes time. So when that sun rises in the morning, it's not an instant, oh, we're hot right away. No, we need hours and hours and hours and hours of sunlight before eventually, by maybe 1 o'clock, 2 o'clock, 3 o'clock, usually that's the norm, anywhere between 1 and 3 p.m., we finally reach, ding, the oven's ready, right? It's preheated, right? You wait for your oven to get hot enough to then put the cookies in. Well, we have to wait all that time in the morning to get the temperature hot enough to reach the peak temperature for the day. And that's, again, because of all what's going on over here. Sunlight goes in, heat comes out. So it's sunlight in, heat out, but that takes time. So this just shows the same thing. Short waves go into the ground. The sun rises in the morning. Those short waves then get absorbed. They have to get converted into heat. And then that lower form of energy, heat, comes out of the ground, infrared. We call that, again, terrestrial radiation. So it's higher energy comes in. That's insolation. This is insolation over here. And then it's infrared going out, heat coming out. And it's this heat that makes the air temperature warm. So it's really the sun's job is just to really give us the energy. That's the job of the sun. It's just to provide the source of energy. That's all its job. Gives us the energy, and then the earth takes it from there. Sun just puts the energy into the ground, and then the earth does what it needs to do, turn it into heat, spit that heat back out, and that's what makes the air warm up. And again, that takes time. Just think of the earth like an oven. Now, it says when insolation absorbed, that means when the sunlight coming in from the sun to the ground, equals, there's the key, equals the terrestrial radiation. That means the energy coming back out of the ground. We are in what's called a radiative balance, right? We're in a balance. We're in equilibrium. Again, radiation just means energy. We're in an energy balance. I use money as an example too. Let's say this month you earned $5,000. All month from the first to the end of the month, you made $5,000. That was your income. Then you had all these bills, your rent, your electric, your cable, etc., etc. You paid out $5,000 in bills. Well, you made a balance. The money you made equaled the money you paid out. You just broke even, right? You're not in a surplus. You don't have extra. You're not in a deficit. You didn't fall into debt. You just made enough. Well, our sun and earth go into the same situation twice a year. Could you tell me, and I'll give you a second, I'll do a little pause, what 2 months would we be equal? When would the amount of energy coming in equal, stressing that word equal, the amount of energy going back out? We're going to be in an equal balance. And the 2 months are March and September. Why March and September? March is the first day of spring. September is the first day of fall. Those are your equinoxes. So we are in a balance in March and September. Old saying, March comes in like a lion, goes out like a lamb. To some extent, that's true. What do they mean by that? That means the first half of March, it's still coming out of winter. It's cold. You might get a snowstorm beginning of March. Winter's holding on. By the second half of March, the temperatures start to turn the corner and we start to get into spring, warmer weather. So, but if you take the beginning half and the end half of March, that equals out. September, same kind of thing, only reverse it. The first half of September, you're coming out of summer, right? You think about when you go back to school in the first couple of weeks. Classrooms are hot. Kids are still wearing shorts and t-shirts, right? Teachers have to put their air conditioning fans on, right? It's still hot in the classrooms. Typically by the second half of September, especially nighttime, it starts to get cooler at night. We're starting to head into fall, right? So it just flipped the other way. Instead of going cold and then to warm, we go warm to cold. But these 2 months, because those are the months of our equinoxes, we are typically in a radiated balance. Typically. We even itself out. Duration. So if you said, what was the duration of the Rose Bowl game the other day? Rose Bowl game, right? Alabama. Duration means how long, right? What was the length of time? So in this case, when you say duration of insolation, you're saying what was the time between sunrise and sunset? Our duration of insolation right now is short, right? We only have 9-hour daylight duration. Very short days. When we get to June, we'll have 16-hour duration. We'll go up 6 hours. We gain about 1 hour on average. We gain about 1 hour of daylight per month. So again, you're not going to notice it today, early January. You will notice it by the time we get into February. When we hit Valentine's Day, you'll say, "Oh yeah, Mr. Ruckel, I noticed now it's not getting dark at 4:30. Now it doesn't get dark till 5:30, 6 o'clock." Right, when we get to St. Patrick's Day in March, now it's not getting dark till 6:30, 7 o'clock. Right, the days start to get longer. We gain about an hour a month until we hit our peak in June. So duration of insolation is just how long is the sun up? How many hours and how many minutes of daylight do we have? Time from sunrise to sunset. Now, what affects that latitude? Where are you? Are you at the North Pole? Are you at the South Pole? Are you at the equator or anywhere in between? And this chart, which might be a little hard to see, I kind of put a red box close to us. This column on the left shows every 10-degree increment, so it doesn't have exactly Rhinebeck, but Rhinebeck is 42 degrees north. That's our latitude. So I put a red box around 40. That's probably, again, close to New York City, but that's close to us. You have your 4 seasons. These first 2 columns, you see I put a box over here, is the summer solstice, June 21. We get up into the low 70s for the angle. So they give you the angle of insolation. That means the angle of the sunlight at noon. So we get our peak sun is around 70, low 70 degrees. And we have about 15 hours of daylight. There's your duration. So that's June, when we get to the first day of summer. March and September, there's your equinoxes. Our sun angle has dropped, right? From June, we're now down to 50 degrees. Sun's getting lower in the sky. But notice duration, and actually notice from pole to pole. Up here at the top is the North Pole, and at the bottom of this chart is the South Pole. Notice on March and September, what's the number for duration? 12, all the way up and down the column. Everybody's getting 12 hours of daylight. We are all equal on March and September. Then we get to winter, which again we just passed a couple weeks ago. Notice where the sun is, very low. Those are those oblique rays. I talked about that in the other video. The oblique rays coming in from the side. We only have a 25, 26 degree sun. And again, we bottom out at like 9 hours of daylight. Notice the poles when we talked about this in astronomy. See the 0. So if you go toward the North Pole, here's right here, 66.5. That's the Arctic Circle. Anything in northern Alaska, way up there, Norway, Sweden, Finland, places like that, northern Russia, they have no sunlight. And right now they have very little daylight. Nothing, not much. Versus the South Pole right now, if you go down to the Antarctic Circle, 24 hours of daylight. They're getting full sun down there at the South Pole right now. When we get to summer, 6 months from now, notice they flip. Take this 0 and put it there. Take this 24 hours of duration and put it up there. Everything flip-flops. Now the South Pole will have no sun, and the North Pole will have the full sun when we get to 6 months from now. And again, everybody's getting 12 on the first day of spring. And again, this has to do with our tilt. Why do we have this situation, right? March and September, our axis is basically straight up and down in relation to the sun. Is it ever straight up and down? No, we talked about that in astronomy. It's always sitting at a 23.5 degree tilt. But the position of the Earth in relation to the sun on these 2 days makes it appear as if the axis is straight up and down in relation to the sun, and that's why we are in an equinox, 12 hours across the board. This would be 6 months from now when we get to June. Notice the North Pole axis is leaning toward the sun, South Pole leaning away from the sun, so the North Pole gets the 24 hours of daylight, the South Pole gets no sun. Again, this will be 6 months from now. Equator, always 12. So again, I know I've had students say, where is the most consistent place to live? Well, it's hot, but it's always a consistent 12 hours. So if you live close to the equator, you have the 12 hours all the time. Today, tomorrow, next week, next month, etc. It's always 12 hours at the equator. This would be a couple of weeks ago. This was our situation. The North Pole was leaning away from the sun. So notice up here, no hours of daylight. The duration was 0. And if you go to the South Pole right now, the duration is close to 24 hours a day of sunlight. And again, the duration is always 12 at the equator. And so in the summer, if you go north, I know I've had a few students, I remember saying they went to Iceland, or you went to Finland or Norway in the summer, or even go to Canada, or even go to Alaska in the summer, you're going to increase your duration, right? Because you're heading toward that 24 hours in the summer. So the further north you go in the summer, duration of insolation increases. Your day gets longer. This time of year, right, winter, if you were to go to Alaska, you would go to Maine, even go up to northern Vermont, New Hampshire, duration decreases. They have even shorter days than we do the further north you go. And then again, everybody gets to 12 hours on the first day of spring and the first day of fall. And that is it for this video. This is the second video. Again, I'm going to post these on my YouTube channel. I'll put the link on Canvas for you to go and access these videos. There'll be one more video. There'll be 3 videos this week. So please make sure you watch them in their entirety. Go back, rewind. If you need any help on a worksheet this week, on an assignment, you can go back and rewind to that section of the video that might help you explain something or find a definition. And I will talk to you soon.